The student is transferring sufficient amounts of dilution into the cuvette to be read by the spectrophotometer. The amount rests directly under the arrow. The student will now wipe two sides of the cuvette, specifically the one with the arrow facing towards the beam. The student will now place the cuvette into the spectrophotometer with the arrow facing towards the beam, and then the student will close the spectrophotometer. The student will now zero the spectrophotometer, and done. The student is now scanning the absorbance of their sample, and then their lab mate is writing down the absorbance in a notebook. After repeating the aforementioned process for each dilution and stock solution, the student is now going to take the final dilution out of the spectrophotometer and close the lid after they take it out. After the students clean their area around the spectrophotometer, they come back to their notebook and outline their calculations and procedures. So at the top we can see the stock solution and the dilutions with their decreasing concentration. Under that we see the absorbance values found from the spectrophotometer, and then using the equation M1V1 equals M2V2, that is how the concentrations are found. And they were plugged into a graph with concentration on the x-axis and absorbance on the y-axis, which we can see right here.
Okay,
awesome.
Okay, so the Beer-Lambert law, it states that the amount of energy absorbed by a solution is proportional to the concentration of a solute and the molar absorptivity. So the equation is A equals EBC, where A is equal to absorbance, E is equal to molar absorptivity, B is equal to the length of the light path or the wavelength, and C is equal to the concentration. So essentially what we're trying to do is we're trying to find the molar absorptivity. So we rearrange the equation where we said E is equal to BC divided by A, and then we find out the molar absorptivity through that. Essentially, if you're going to look at the relationship between the concentration and the absorbance, the higher a solution's concentration is, the higher the absorbance rate is. And failure to like zero the solution, like putting in the water and putting in the blank, you would get a wavelength that is different, which would completely mess with the equation because that would lead to a different absorbance rate.
Okay, so I'm going to be talking about comparing and contrasting quantitative and qualitative data with the spectrophotometer. So first I'm going to give two examples of why it's important to read across all wavelengths when using the spectrophotometer. So first, if one absorbance or dilution that we look at has an absorbance, a lambda max absorbance of 200 nanometers, and we only look at it from 600 to 800 nanometers, and we would miss the lambda max, we might find no absorbance between 600 and 800 nanometers, or we might find a smaller absorbance than what is the actual lambda max. Likewise, for the second example, if there was a dilution or stock solution which had a lambda max in between 200 and 500, and we only measured it in between 100 and 150 nanometers, we wouldn't find the lambda max in between that 200 and 500 nanometers, resulting in a different absorbance value, which would be used incorrectly in the Beer-Lambert law. So adding on to that, it's important to explain why we need to scan across all wavelengths. So using those two examples that I just gave, we know that it's important to scan across all wavelengths when using our solution in order to find the lambda max that is correct for the solution that we're doing. The lambda max being the rate or the highest absorption rate that is there, or the maximum absorbance rate that is there for the solution.